Let's look at some examples now. In the previous one, we looked at how we replace these supports with forces that the supports would potentially apply to the body. Okay? So let's look here. Here we have a truss. There's our truss. We have a force being applied there. This is an applied force. And you can see that there are these potential reaction forces here. Okay? So we need to, the truss is our free body, or rather, the truss is our body, which we want to draw a free body diagram of. We want to free this body, okay? We want to free it. But we need to draw the forces that act on the body. Okay, so what is this? This is a pin connection. If you look at the previous video, you look at the previous table, diagrams, you'll see this is a pin connection. So this type of connection can potentially resist both horizontal X direction motion and vertical motion. So we need to put in AX and AY over here. Now the roller connection, the roller support, can only resist vertical motion. So we only put in BY. And then of course we have P over here. Now, so I hope that's clear. You replace this with the forces that it could potentially apply. I want to make this clear that when you actually do the calculations to calculate the values of these forces, sometimes you might get an AX equals 0, for example. And then you're like, but why did I put that in there? Remember, a pin connection or any support, there is the potential, right, for applying a force in that direction. It doesn't mean that it necessarily does apply it. It all depends on what the applied forces are doing. So you may find a scenario where there is no horizontal force, even though when we are drawing our free body diagram, okay, we need to put in all the forces that this type of support can potentially apply to this. Okay, why do we do this? Because we need to use this information to say some of the forces is 0, and then we say some of the forces in the X is 0, some of the forces in the Y equals 0, and some of the moments about a certain point, right, equals 0. And so we then use all the forces that we've identified and we put it into that left-hand side. All the forces in the vertical, we put it there. All the moments about a certain point, and we put it there. And we can solve for any unknown forces. Okay, the second thing that I wanted to point out is, you might be thinking, but now what about these forces between this member and this member? Or the force between this and this member, okay? Because clearly there's potentially either a compression force here, or they're pulling on each other, there's a tension force. Well, the whole thing is that this is internal. These are internal forces. And internal forces cancel out. They cancel out. So you can go and put all those internal forces into that equation right there, but they're going to cancel out. So we only care for what is happening externally to the mechanical system we're interested in. Okay? Now, if you were interested in just that member there, then you would make that your free body diagram. And then you would need to take into account the force of this member, that member, all these forces acting on this member here. Okay, but we've chosen the entire truss as our system, and we want to determine what forces are acting over there and over there. Okay. What about a cantilever beam? Here's an example. You've got these applied forces here, and you've got the reaction here, the support here. You need to replace this with what? With this set of forces and couple moments. It resists motion. It can potentially, okay? That's the word. Because you might calculate a force and you say, but why is there no force there? I calculated F equals 0, for example. All we're saying is it potentially can apply a force there. you need to go and calculate them using these three equations to see what the value of these forces are. So we replace this with a force F, a vertical force V, and a couple moment, because it can also resist motion in the vertical and it resists rotation. What about this beam here? We've got applied forces, P, we've got an applied couple moment here, and then we've got supports. A is resisting motion and B is resisting motion. What is B? It's a pin. We replace this with Bx, By, and this, it's called smooth surface contact at A. So remember, if you had smooth surface contact, what did you do? You removed this and you replaced it with a force perpendicular to the surface. Okay, so there is the surface, and we apply a normal force perpendicular. And now we've got our free body diagram. And don't forget, guys, you also need to apply or insert your XY axes. Remember, we're looking at 2 dimensions in this section A. Whoa, now look at this guy. This is a very complicated system. Alright, very complicated. Member there, a member there, member. It's got a pulley here, it's got cables, it's got this weight over here, it's got an applied force there. But all we're interested in is we're interested in the entire system as a single body. So we draw it like that. We don't care what's happening on the inside. We don't care. Right? It's internal. We only care is if we just want to isolate that member, for example, or that member, then we care. But all we're caring about is what's happening in this specific case, what's happening external. So this is a roller. So I apply a AY there. There's no support reaction in the horizontal direction. This is a pin, again, BY, BX, and we have this weight over here, mg, and we've got this applied force. So this entire mechanical system we take as a single body, and we draw a free body diagram. Does that make sense? I think that's all that I want to show for now. Okay, see you in the next one.